All right, today I'm covering two sets of topics. One is a practical type topic. Actually, two sets of topics. One set's practical. One is something I forgot to talk about earlier. It's going to take me like 2 minutes to cover. Then I'm going to talk about set operations. And then for the second half, it's back to some theory crap that we all enjoy so much. But it's what it is. The upcoming dates as applicable. Assignment 2, November, next Monday. Hybrids are the Monday after, as is the second test. I will be assigned on that day, not due on that day. Labs, should be working either on Lab 9 this week or Assignment 2. There is no officially assigned lab this week. So if you want to do 9, great for you. You get ahead and you get a week off somewhere. Or you can come in and talk about Assignment 2 if you're confused. My lab times are posted on a Blackboard, so if you can't make your regularly scheduled lab, you can come to one of the other ones. First come, first served basis, as room is available, as usual. Okay. Now, see if I can get my camera to actually look somewhat straight. All right. Now, the first thing we're going to talk about is I forgot one little bit when I was talking about aggregates. You guys remember when I was talking about aggregates? That was last week, I think it was. Maybe the week before. I was talking, doing sums, min, max. Yeah. And then I showed you guys how to use subquery to aggregate and aggregate. I forgot one last clause that may be tested upon later. And that is how to filter based on the results of an aggregate. I'm actually going to do this demo mode. I'm going to sit here and demo up there as I discuss it. Okay, so essentially what you have to do, I don't know if I can get my mouse going to the right place, that'll work a lot better. All right, so you've seen this kind of aggregate before. And I did also showed you how to do something like this. So what this will do, as a quick reminder, is it's going to add up how many order lines there are per order. Fairly straightforward. That's nothing out of the ordinary. However, let's just say I want to know where I want to actually do some filtering. So I don't want orders that only have one product in it. There's a new clause that I haven't shown you guys called. It's called halving. And halving is you can go count of star greater than 1. If you look down here, you'll see there's 2, 3, 2, 1, 2, 1, etc., etc. When I run this thing now, it gets rid of the ones. So that's the halving clause. You can use a subquery in this if you want to. You know that big example I did at the end of last week, that subquery inside a subquery that's joining a subquery? You could actually simplify it a little bit by using the halving clause. So you can actually do where the average of the sum, like the average is greater than the sum kind of thing. You could just do it as a subset. You could probably get rid of one subquery out of the whole process. Other than that, halving behaves just like the where clause. It is the last thing to be processed. So when you think about the order of operations, or the order of the language, it always processes the select first, then it processes the from / join, then it processes the where, then it processes the group by, then it processes halving, and then if you've got an order by, goes last. That's the order of the language for the select statements. If you can remember this order, it's fantastic. essentially, as you're writing SQL statements, if you can follow this order, you shouldn't have any problems with you trying to do the wrong thing at the wrong place, or trying to do the right thing at the wrong place, or doing the wrong thing at the right place. Essentially, there's 6 pieces, and it's listed like that. Any questions about how halving behaves? It's pretty straightforward. It's just like the where clause. It just happens later. Basically, the purpose, like I said earlier, its purpose in life is to allow you to filter on the results of an aggregate. And what's cool is the halving clause, the aggregate in the halving clause doesn't have to be the same as the aggregate in the top of the query. So for example, let's say I want to just do the total of an order, of all the orders, for orders that have more than one item. So I can actually do a sum at the top, and then in the halving, we're in a separate aggregate. So it would look something like this. Great. And you can see here's the sum. If I actually were to put the count of star on here, you can see that it is respecting the orders have more than one with the sums. So it allows you to filter out the crap. Okay. My camera's really crooked. Don't know why today. All right. Any questions about halving before I move on to what I was supposed to cover today?
Does that lighten the load on the processor?
Hey?
Does that lighten the
It lightens the scanning of the tables, but it adds to the actual processor use. So it's a trade-off. The processor is usually faster than the disk access, so it's usually it's a trade-off to the positive side of it. And on the other hand, if you're trying to do it in Java, you'd retrieve everything and then loop through it in Java, doing if statements for every single row. I can guarantee which one's going to be more expensive to run. Okay? All right, so that covers that. Now, I'm going to talk about unions next. And actually, set operations. Not just unions. Okay, now if you remember when I was talking about joins last week, and I was talking about how people use Venn diagrams to describe joins, but you shouldn't, because joins aren't set operations. What I'm about to do are set operations. So here come the Venn diagrams for everybody's enjoyment. Who here knows what a Venn diagram is? Good. How many of you have seen them on Reddit? See? Who says Reddit's good for nothing? Okay, so in SQL, there are 3 common set operations. There's a few actually others, but the 3 that people use the most are union, intercept, except / minus. Depending on the database server, some use the word except, some use the word minus. Essentially, the purpose of what the set operations do is it takes a complete query, and then you take a complete second query, and then it actually does the operation between the two. So you run 2 full queries, and then it takes it and plays with the results of 2 queries for you, so you don't have to do it yourself. And I'm talking, this could be as complicated a query as you want, but there are a few basic rules when you're talking about set operations. The biggest one Crap, I can't write today. Okay, the first rule is they have to have the same number of columns. In other words, if one query returns 3 columns and the second query returns 2 columns, you can't run a set operation on it because they don't have the same number of elements. Does anybody here remember doing set math in high school? Vaguely? Some of you might. It's funny, the exchange students are all going, yeah, I've done that before. Canadian students are like, what are you talking about? Go Canada education system.
Sir, it's a boot, not a valve.
Hey?
It's a boot, not a valve.
Oh. It's moose, not mooses. Yes. So, they have to have the same number of columns because you can't run a set operation on dissimilar data sets. So if your query returns 2 columns, guess what you have to have on the other side? 2 columns. Number 2. Let's try writing this properly. The columns must have similar data types in the same order. You can't do a set operation on numbers versus strings because it's not the same data type. Therefore, the math doesn't work the same. Math on letters and numbers compared to just numbers is not the same. Therefore, if you have a column with a number and a column with a string, in the first one, the second one has to have a column with a number, column with a string in the same positions. As follows. If I were to return, how far over am I? If I go ID being an int and name being a varchar, they must have this, the second set, third set, fourth set must all have the same. Thus, ID is an int and name is a varchar. And then there is a third rule. The third one is columns must have the same names. I know the writing's off the guys in the back, but yeah, the columns must have the same names. If the columns don't have the same name, make sure you alias at least one set of data to match the names everywhere else. In other words, you can't have ID and name and then ID and description because the sets aren't the same. The data might be different, but the actual structure of the set is different. The structure of the sets must be the same. Actually, when you're working with set operations, this is the hardest part. Is make sure everything matches out properly. Number 3, you put a little star next to it. MySQL doesn't care. MySQL also doesn't care about the data types. It'll try to do a union on a data set, whether or not the data matches. And it'll give you results. Totally invalid results, but it'll give you results. Also, MySQL doesn't support these two, which is why we switched away from MySQL. You can't teach proper set operations with MySQL because all it supports is union. Mind you, union is what's used 90% of the time, but they don't support the other two, which everybody else does. All right. We're going to start with discussing the union. The union, and by the way, this is lab 9 that I'm talking about today, just so you know. What union does is it grabs all the values from A and grabs all the values from A plus any values that are unique to B. So what happens is it says gather everything from A and then anything else you found in B, so that you can get all the unique values from two different queries. The most common use for this, collecting email addresses, or sometimes it's comparing products. I'll do actually an example up on the screen. So here's our customers table. And actually, I'm going to just run this because I don't remember the structure of this table offhand. This one's not in your ThinkCube database yet. It shows up when you do Lab 9. And here's an email in this one also. So if I run this, also, you can see there's just the email addresses for one and the email addresses from the other. So the first one has 10,000 rows. The second one has 1,300 rows. Now, if I want to do a union, you take one query, write the word union, write the second query. Then you run it. I end up with 10,964. Do you notice it's not, if I add this one up, which was 1,300 rows plus the 10,000 rows, the numbers don't add up, right? You can't take set A plus set B. It's set A plus whatever's unique in set B. And that's what union does. That's literally is. That's all union does. Now, if that's union, there's intersect. Actually, I forgot to write. There's a second way to write it. There's also intersect. They're the same thing. Just so happens that Postgres uses intersect. So exact same query. I'm changing the word from union to intersect. Now I have 459 rows. Intersect says, give me the rows that exist in both tables. So this is to find the overlap between two sets. Intersect gives you this. Union gives you everything of A plus anything you find in B. And then you've got the last one, which is except. Intersect gives you everything that is in A except anything it finds in B. So you just want to find what's unique in A that's not in B. So now I got 9,600 rows. That's the yeah.
Is the first one you rate your A? Is that how it goes? Like, how do you know which one's your A and which one's your B?
A, B, C, D.
But it goes in order.
It goes in order, alphabetically up and down. Well, I wouldn't be called A. I mean, in this case, I could call it customers and trade show leads.
Yeah.
But essentially, set A operator set B. You can have as many set operations as you want. Theoretically, you could have A union B, union C, except D.
Okay.
And it starts from the bottom and works its way through, unless you put brackets in it. Then it does, obviously, it does the brackets first, and then it works the rest out. So in theory, you could build up email lists from like an email list from A, B, C, and then maybe they say do not disturb list. So you want to go A, B, C, except what you find in D. So you just keep adding and adding and adding to your set of operations. But essentially, that's all there is to set operations is 3 keywords. All the examples you need for the lab, it's all I ever ask you to do is 2 sets: A set B, customers and trade show leads. And that's what the sets do. Then, of course, I didn't do the coloring for blue in here because there's only so many colors. Like that. I don't know how to describe it. There's something here. Those are the 3. There is one other called Union All, and Union All is the most useless query of them all. What does it do? $1,100. 11,429. Basically takes set A and adds set B to it. And doesn't return distinct values.
City.
It's not very useful. But it exists, and I'm sure it has purpose in life, but I don't.
It's such a small purpose that it's not used.
Somebody found it useful, so they created it. Okay. Okay, those are all the set operations. Does anybody have any questions about the set operations? When it comes time for the exam, I think there might be 2 questions about set operators on it. Maybe 5, but I think it's more like 2. Just a couple. It's not a big topic. It's not something you use on a regular basis. But you'll hit the odd moment if you do work with databases in your career that you will need to use it. As long as you understand that your Venn diagrams, you're good. That's it. Okay.
So what was the union again?
Union grabs all the distinct values from the 2 tables. So everything from A plus any new values from B.
Oh.
Intersect gives you the values that are shared by both sets.
Okay.
And except gives you all the values from A that aren't in B.
Oh.
So intersect chops out a chunk. Except chops out a chunk. Intercept gives you a small subset, and union gives you everything from A plus any new values from B.
So union will pretty much give you everything.
It'll give you everything that's unique. Distinct values between the 2 tables. That's what it's really good for when you're dealing with large email lists, for example. That's where you'd want to use it.
Okay.
If there is a value in A and the same value in B, during union, will you put it 2 times or just once?
It'll give it to you once, and it'll give you the version from A. Not that it makes a difference because it only gives you 1 value, but it'll give you the 1 value. I've seen it done that you can help determine which one it's from by adding a second column to your union, like a fake column. Something like such. If I go you see this shows all customers, and then you'll see all leads at the bottom. So there's everything from A, plus anything it found in B.
Oh, okay. That's good.
That's one way to, if you really need to know what data set it's coming from, you just throw on a string. You can display strings that to your heart's content as part of SQL. You just put it in quotes. It just treats it as a singular value. Okay. Actually, that was a union all. I did a union. This will do the same thing. There we go. See? There's a leads. I'm sorting it alphabetically. Ish.
So union and all would actually be better there if you want to know the leads at the bottom and the customers at the top. Here is mixing it.
Theoretically, you could just wrap everything in a bracket, treat it as a derived table, and sort on the results if you want to.
What are you doing without the making those strings or adding that column? You got like 10,600 something, and now you got 11,000.
Yeah, because now they're distinct. There's ways of making it behave, but it's challenging. Basically, when you do this, every time you add a column, you're adding more distinctness to it. Definitely wouldn't recommend doing it this way, but there's ways to make it behave. Okay. PowerPoint time. Yay. All right. I'm going to kill these lights. The screens are a little brighter, so we can try to keep everybody's attention focused. All right, 22 slides. Let's see if we can get through at a decent pace. All right, performance tweaking. For those of you that have already done the hybrid that points to chapter 5, this will be reviewed. Those of you that haven't done this hybrid yet, you probably should get around to doing it. Putting the thought out there. This is about different performance tweaks. All right. So far, I've spoken to you guys about normalizing your data, breaking it down to the smallest possible chunks. Sometimes for performance reasons, you actually got to go back a bit, take a step back from properly normalized data because their data gets too complicated and the queries take too long to operate. Servers nowadays have so much horsepower that this is a minor concern. What if you're working with huge amounts of data? It probably makes a difference. So the process is called denormalization. So you're taking normalized data and you're turning it into a non-normalized structure. You can improve performance, as I was just saying. In other words, you're reducing the number of joins, you're reducing the number of table scans. The less processing the server has to do, the faster it's going to run. Which one's faster to put together? A piece of furniture from IKEA or getting someone to deliver a chair to you? The chair gets delivered to your house is going to be faster because you didn't have to take the time to put it together. Unless you're a freak and you can assemble IKEA furniture really fast. Or you've bought too much of it. Now, there are some side effects to denormalization. There are costs because it wastes storage space. And realistically, this used to be more of a concern back in the day. And this is where this textbook shows its age a little bit, where they start worrying about space. I mean, if a company is worrying about space nowadays, that means that they're putting in lots of money, therefore space shouldn't be an issue. It's a balancing act where how much space do we need to cover the needs of our business? And if you're cheaping out on disk space, you probably have bigger problems than what you expect. The biggest concern, though, is the danger to data integrity or consistency. The point of normalizing your data is to make sure that everything is self-contained and changes in one place don't affect something else. When you start denormalizing the data, what happens is what's the word I'm looking for? When you start denormalizing the data, you start having duplicate data again, and suddenly that whole update anomaly business and the delete anomalies start creeping back in. But there are a few chances where normalization makes a lot of sense, and I'll show a couple right now, actually. Okay, here's an example. This is straight out of the textbook. actually. Here's one where you could denormalize student ID versus application ID. Any given student can apply once to a college, to a given college, theoretically. That's the theory here. I know you can apply to more than one program at a given college, but usually it's, I want to take course A, course B, or program A, B, or C, not 3 different applications. It's one application and 3 choices. So in this case, each student gets 1 application. There it is. So if you were going to normalize it, or denormalize it, you'd take their application date and their qualifications and put it all as part of the student record. That means you don't need to do a join, you don't need to do a table lookup, it's all in one place. Sometimes it's better to normalize your data just to make things simpler. I mean, Algonquin, how many students do you think is in their database? Any given year, there's over 10,000 students registered, and they've been operating for, what, 25, 30, 50 years? 1950s, I think it was built. Right, so it's been going around for a bit. They've got an awful lot of students in their data and their records. So the other choice they have is a many-to-many relationship between vendors and items. In other words, a vendor has many items, and you can get the items from many vendors. For example, a folding chair. A vendor could sell 3 different kinds of folding chairs, but you might sell 6 kinds because you get 3 from one vendor and 3 from another. Essentially, as they show the example here, all they did is they got rid of the price quote and they collapsed it into a single entry. Why? It speeds things up. The only thing that actually gets duplicated is the description. As you can see, the vendor ID happens here. If you collapse it up here, the vendor ID goes up here, the item ID is already up here. The price doesn't get duplicated, but the description gets duplicated. And that ends up being, you know, the denormalization. You do that for performance reasons. And then the last one is the one-to-many. And this one's iffy. I'm not a fan of denormalizing one-to-many relationships. The only time you do it is for literally speed, for reporting purposes. Essentially, in this case, is you got storage instructions for given items. So it could be multiple, a single instruction has multiple items. For example, how many of you have bought desks at IKEA recently? You know, some of those desks comes in 3 boxes, right? A, B, C. And the PCE is actually C, and they don't have any. That's at least the experience I've always had. And they could be that this item has, you know, this set of instructions has 3 different items attached to it. And you can actually normalize, that's the normalized here, right? Where you go, what container store type, what store it's in, and then you got the items. You could also denormalize it so it's all in one row. For companies the size of IKEA, they probably want to denormalize. Why? Because it runs faster. The biggest use for denormalization, however, is in data warehousing. For example, I always like using Amazon because most of us have bought something from Amazon, or at least shopped on Amazon. What happens with them on a daily basis, all the orders that get processed get collapsed down to simple records, simple, you know, 1 or 2 dimensional records. They get pushed into a data warehouse for reporting purposes. So at the end of every day, they actually do a summary record that they store that's non-normalized, because it's really, really easy to run reports on that. It has graphs, you can do graphs, you can do summaries really quick. The fewer joins you have, the faster they run, so they can do more analytics. So data warehousing and analytics, as in, you know, you're running reports on the data, that's when you denormalize for reporting purposes. I can guarantee that your sales managers don't want to wait 2 hours for a report to run. If you can write a routine that denormalizes the data on a nightly basis, and then they can run it in 5 minutes. All right, so the dangers of denormalization. It increases your chances of error and inconsistencies. In other words, you don't want your denormalized data to be read-write type setup. You want it to be read-only. as far as the user application is concerned. You take the data, you denormalize it, so it can be run reports against it. That's a read-only environment. The only time that stuff gets written is when your application does it, not an end user. It brings back the good old anomalies that we were trying to get rid of in Lab 5. You're bringing them back in. And then when business rules change, you end up having to rewrite parts of the application, which sucks. Now there's a few other things you can do instead of denormalization, and I'm going to cover some of it in a moment. Okay, partitioning. Now, partitioning, I don't mean by partitioning like your hard drive, where you can take your hard drive and cut it up into smaller chunks. Although nowadays almost nobody partitions their hard drives. But there once was a time when there was a partitioning your hard drive, especially when the drives were slow. And your OS could read more than a 1 gigabyte partition. There was a time.
Shitty time.
Windows 95, one more than a gig. Good luck. But that's, that's not the kind of partition. What we're talking about is horizontal versus vertical partitioning. This is also in chapter 5. Now, horizontal partitioning, you take the data and you break it down into smaller chunks across multiple tables. You end up with lots of one-to-one relationships. So what happens is sometimes there's certain records in a given record that there's certain columns that are always queried together, such as name and address. And then maybe you have another column which should have their common payment options, which could be in a separate table. And you have another table that has their preferences in it. That way, usually when you search for your preferences, you want all your preferences to come up at the same time. Whereas you might want to have all their address information come up at once. Rarely will you pull open maybe their payment information and their preferences at the same time. Theoretically, you could, but normally you want to treat that as two separate transactions. The other advantages also is if you want to separate the data also in separate rows, broken down by dates and times. Actually, I was talking about vertical first. Got confused there for a second. So yeah, vertical, you break the columns going sideways. Horizontal, you break them going this way. Horizontal is good for if you need to have different access levels. Finance versus HR. HR doesn't always see how much you make, whereas the payment people see. Or your HR person in your department may see certain things, but they don't see your payroll, because that goes through payroll department. It's a bit like that here at the college, where our benefits are administered by one department, but our payroll is administered by a different department. One floor upstairs. They're not even in the same office space, they're in 2 different rooms. So horizontal partitioning would be if you want to allow certain people to see certain chunks of the data, but not all of it. And the vertical partitioning allows you to split the table up across multiple columns. Now, partitioning pros and cons. The advantage, it's more efficient. In other words, records that are used commonly together are grouped together. So in other words, it's as if I separated this room into 3 groups, right? Partition A, partition B, partition C. And I needed to say, everybody over there do one job. You guys do a different job, and you guys do a different job. And you all actually did what I asked you to do. It'd be more efficient than say, okay, you, and you work on something together, but you're not allowed to move from where you're at. Whereas if you're already all in a cluster, you can just turn around your chairs and talk. Local optimization. Each partition can be set up to have its own rules for performance. In other words, I could say, okay, well, you guys are all going to work together, you can go sit in the hall. So your noise doesn't interfere with these guys. And then I could say, you guys go to the classroom next door and work over there so that your noise doesn't interfere with these guys, so that the volume level is separated between different groups. That's what that does. You can have your own rules for each group of people. Same thing with the database. Security. If all of you guys are in one room, and all of you guys are in one room, And for example, let's pretend you guys are all Howard students for lab, and you guys are all Kumari students for lab. I know it's a different group, other teachers, right? And it just so happens that Howard's not allowed to see Kumari students, and Kumari's not allowed to see Howard students. What happens then? If you're in separate rooms, you can't see each other's students. Thus, it improves security because they can't go to the other person's room. Recovery and update and uptime. Smaller sets are easier to deal with. One of the reasons I don't take physical attendance with lecture sections, how long does it take for that piece of paper to make it all the way through the room? Or even better, if I were to call out each person's name while I mangle your name, how long would that take? As opposed to, if let's say I took attendance in labs, which I don't, but let's say I did, it's a lot faster because I can just say, well, okay, well, there's 26 of you in here. Let's go through it. It'll take, what, 2 minutes? As opposed to 100 students, 120 students, that could take 15, 20 minutes. It's a waste of time. Load balancing. Since you're all working in different areas, that means you're not interfering with each other's resources. Theoretically, if these guys are in one room and these guys are in one room, they're probably on different network routers and different network segments. Therefore, your work is not interfering with each other. However, there are some disadvantages. Maybe you guys are in a room where all there is Wi-Fi, and all you guys are in a room where all there is wired. The wired is usually faster than the wireless and more consistent. Therefore, speed. Sometimes with partitioning, you end up with partitions on different disks. One partition could be on SSD, the other one could be on a spin disk. The SSD is faster than the spin disk. The problem is with partitions, they're non-transparent. That means that you have to write your application understanding that the data is broken up in pieces. You can't just go select star from students. I got to go from select star from student block A, student block B, student block C. And since they're coming from different places, the database server has overhead trying to assemble all the results. And there's always extra space usage because sometimes you have to have duplicate data. Now imagine if you're all in 3 separate rooms and I was in all 3 rooms at the same time, somehow. I managed to clone myself and send myself off to each room. That means you're occupying 3 DANs instead of 1. Okay. I'm not going to go over this one. This slide actually included in here, and I'm going to put the slideshow up. Please read it. I don't cover Oracle in specifics. I try to stay away from the specifics as much as possible. However, there's a few things in here that are important. Okay, vertical partitioning. That's the distribution of columns into separate physical tables. That's what I described earlier, where I take you guys, put you in one room, take you guys, put you in one room, put you guys in another room. That's vertical partitioning. So the table's cut up in pieces like this. That's how vertical partitioning is broken down. It's one table, but it's been broken down into multiple pieces. So when it's partitioned, if you do a select star, it's only going to return partials, which means everything runs faster. I can also say, well, students over here are only allowed to see these 3 columns, and students over there can see these 2 columns. I can separate between what people are allowed to see based on the partitions. What happens is it reduces the demand on individual pieces. But there's always issues, like everything else. Because what happens is, if it's broken down, and this basically becomes 3 separate tables, you end up having to use joins between everything. which is gross. Not a common thing you need to do until you get into large-scale data sets. All right. Designing physical database files. Yay. Okay. The physical file is what's actually physically on the disk. And essentially, when you create a database, the files go into a spot on somewhere on the disk. If you don't change any settings, all the files from a given database go into one place. You can't really control what happens with these files by default. However, some database servers allow you to use something called table spaces. I can create table space A, and I can put table space B and table space C, and I can actually put each of those on a separate hard drive so that I can access multiple parts of the database coming from more than one hard drive. Can anyone take a guess what the advantages of splitting the database up across multiple disks?
Higher speed if you're taking from a certain part of the disks.
Well, it's not just that, it's faster I/O. Because let's say you have customers on disk A and orders on disk B.
Yeah,
When the database server asks for data from customers and orders at the same time, it's actually going to pull the data from two different sources at the same time in parallel. Whereas if it's all on one disk, it'll go, give me everything for customers, now give me everything for orders. Whereas when it comes from two different disks, it says, give me everything for customers and orders. And it comes in. It improves the I/O. Same thing when it's time to write to the disk. The slowest part of any disk operation is writing, especially with SSDs. They're half the speed of reading. And if you write to separate disks, that means it's updating the data in 2, 3, 4 different places at the same time, as opposed to update all the customers, now update all the orders, now update the order lines. Whereas you can say update the customers' orders and order lines all at the same time because they're in separate tables. Separate disks. That's the purpose of the table spaces. You can use it for segments or extents. In other words, you can set up just a certain space of the disks, the files, so they all exist side by side. Some of them you can arrange them to exist on different disks. And then you can actually arrange it with some database servers, such as Oracle. You can actually do data blocks where certain columns are stored on a different disk. Oracle allows you to tweak it to your heart's content, which is why it costs so much money. It's by far the most configurable database server. It's just painful to learn how to use. All right. There's file organization. There's different kinds of ways of organizing your files. And the commons are heap. In other words, the tables get created any which way, in whatever order. They're sequential. You put files next to each other that are used commonly. Customers right next to orders. Or maybe customers and locations right next to each other so that when the disk starts reading, it doesn't have to jump back and forth. And then there's the indexed approach and the hashed approach where it looks at how the data is arranged and it actually starts breaking up the tables piece by piece so that it writes the customer record here and then part of the address location, then some more customers, some more address. So it's on the disk, keeping the records that belong together clustered together on the disk. Some of this is becoming slightly irrelevant nowadays. This was really important when you were dealing with hard drives that spin. Because, for example, the closer you are to the outside edge, the faster the disk spins. Therefore, you want to store as much of your data at the outside edge of the disk as opposed to the inside edge of the disk. Because the seek times are faster on the read times are faster on the outside, but the seek times are faster on the inside. So you want to you put your indexes on the inside and your actual data on the outside. So the heads are constantly jumping back and forth. Nowadays, with solid state drives, there's no mechanical parts moving, right? It says read data. Okay, they're in blocks A1, B2, and C55. It reads all three at once. That's why SSDs are so fast. Normally, you worry about the file organization because of the retrieval speed, efficient use of your storage space. In other words, you could dedicate a hard drive just to holding database files, instead of having mixed with the rest of the OS. That way, you're not wasting precious OS space for database files. Or maybe you're going to get a really fast hard drive for the database and just have a slower drive for the main OS, because who cares how long the OS takes to boot? Because once the database is running, it's actually read access to the database files. Therefore, you might want to put that on a faster disk. For example, at work, we boot all our OSs off these old hard drives, but the databases are all stored on SSDs. So we have a bunch of SSDs that have been striped, and it just writes to that, and that's where our database volume is on these SSDs. Therefore, you don't have to waste arguing over the hard drive space or the bandwidth, limited bandwidth to your disk that a single disk environment has. Yeah.
Wouldn't that change the longevity of your drives?
Oh yeah, databases kill SSDs.
Yeah.
They take them and chew them up and spit them out for breakfast. Now you do want to get enterprise grade SSDs for a database, or just have a big pile of them, so you can swap them out as needed.
Or a very long extended warranty.
Right?
Or a long extended warranty.
Well, yeah, but if you lose your data, you lost your data, right? So you end up having to have them in a RAID array
Yeah.
with several hot disks, so you can take one out and replace it right away without losing any data. Having your file separated also accommodates growth, because you can clone the hard drive to a bigger hard drive without affecting your OS. Security from unauthorized use, I always find that one arguable. Because to say, well, you know, we have it on a separate drive, it's safe if somebody hacks the server. Take my word for it, once they have root, there's nothing to help you. Once somebody has administrative level control of your server, you can have as many disks hidden in your server. That's our joke at work. You know, we used to have the policy that every database had to have a different different password. We're like, really? How many of you here have had to fix your server because you forgot your password? I think there's 5 or 6 of you now, right? I had administrative access to your hard drive. I don't need a password to get into your machine anymore, into your database. Why? Because I changed the config. So, you know, that whole security side of separating our data to separate stacks, not such a good argument. Because if your database server can see the data, so can the person that took over your machine. Unless they physically, you know, stole the hardware and they just don't realize that it's a network attached storage, that might be a time they care. All right, there's some organizations here. Sequential file organization, every single time you want access and stuff, it has to scan from the top and work its way down. And then if it's a heap, it's number of records divided by 2. In other words, a heap there's no given order, so it just starts skipping through it and eventually it'll find what you want based on the search algorithm. There's complete examples in the textbook on it. There's definitely better examples. I'm covering it because it has been covered. Realistically, this is not something you learn until you learn some of this in your elective database course. You learn more about this in there, just so you know. All right, indexes. Indexes are a way to speed up the access to the database. I think I spoke about them already a little bit, start of the term. Now, probably most of you aren't old enough. Normally I say young enough. Most of you probably aren't old enough to remember card files at the library.
Yes.
Yeah. Okay, how many of you actually remember this? How many of you, yeah. How many of you spent time at the library replacing index cards because you had detention? Because you threw a Super Ball and smashed a bunch of overhead lights. Been there, done that. That's where I used to spend my detentions, was in the library, retyping up the index cards. Because for those of you that remember, you know, you'd go, oh, I need to find something on this topic. So you'd go over to the big set of files and you'd look for, topic starting with C. And you go, C, cat. Right, there's no card for catfish, and you see the remnants in the bottom. Somebody ripped the card out to go find it, right, instead of writing it down. Yeah, that. But that's an index. That's how indexes used to be done. Actually, most of the time it was faster to go ask the librarian, which is where computer indexes, the concept works like. The librarian is closer to a computer index than those card files were. The card files help you organize the data in a searchable manner that's relatively quick, or you could just go ask the librarian to go find you a book on, catfish in North America, and she'd go, go look at, that row. And I don't know how they memorized it, but they knew where everything was in the library.
Because they put all the books away themselves.
Yeah, I know, but they still knew exactly without having to remember where it was, like right off the top of their head. So, indexes and database servers, its purpose in life is to make searches faster. Now, there's a few that happen automatically. Primary keys are automatically indexed. You create a primary key, it creates an index. Why? Because if you're searching for things using the primary key, you probably want an index so that the searches are faster. You can also index certain other things, and these are also known as secondary keys or non-unique keys. For examples of this would be a foreign key, so that you can do a lookup when you do a join, so that they're both indexed so the server matches up the results faster. Phone numbers could be indexed. Email addresses could be indexed. If these are things you search on a regular basis, you probably want to index them so that the searches go faster, because the indexes enable searching to go faster. Okay. Now, the most common type of index is a binary tree. And I'm guessing that most of you don't know what a binary tree is. It's probably a safe guess that you don't know what a binary tree is. Okay. Let's just say we have values A, B, C, D, E, and F. The way the binary tree works is it takes each set of values and divides it. And it does number of records divided by number of values. So for example, it would work better if I had more G, H. It works a lot better when you're in the hundreds. But let's say we have 8 values right now. So the way the binary tree would work is it would say set A is A to D. And then the second set would be E to H. That is the worst arrow ever. E to H. That means if I go select star from customers who are named like Dan, it doesn't need to scan anything on this side. It only needs to search through the first half because D's in here. Then what it does, it'll take this set and divide it again. It'll do A to B, C to D, and then ditto over here. So it'll hit this index, binary tree says, oh, hey, it's in this set, it'll go down. Okay, now it says the first value is between C and D. It'll go down here, and then this will take it again and break it down into C's and D's. That means that by doing a quick lookup in the index, it knows that it only needs to search this set of records. So instead of searching through 10,000 records, it might only need to search through 100. Thus, the searches are fast. That's how binary trees work. That's a tree search. I don't know specifically, but it's the same idea, where you arrange your data based on subsets. The other one's a join index. This example's brutally gross. As you can tell, these are the slides straight out of the textbook. That's the one the other sections are using, so I have to give these slides to you guys. That's why it's these gross slides that I don't like. They don't explain stuff very well. Essentially, all it's doing is it indexes the columns that have things, the columns that have points of commonality, so that the searches work faster. That's all that's doing. Now, it's a really busy slide, and when I post this slide to Blackboard, you'll see there's got about a page and a half of notes I'm supposed to read to you. And that page and a half of notes is literally the page and a half that's in the textbook, word for word. So if you've done the hybrid, you've already learned this stuff. But there's certain advantages. If you're using a heap, it requires sorting. It tells you what's good and what's bad. If it's a heap, adding a new record is good. If it's sequential, you have to rewrite the file. For example, sequential indexes, right? If you have a record that's, let's say right now the database is A, C, D, E, F, and you use sequential. And I want to insert a B. I have to rewrite the whole file again. A, B, C. And rewrite it from the top because you're adding a new value somewhere in the middle. Index, as long as you've got room, you're good to go. The catch is indexes take up 1/2 the amount of space the table does for each index. So, for example, let's say we have a field that is 50 characters long. So that's 50 bytes. And we have 10,000 rows. So that's 500,000 bytes. The index, because it uses the B tree, will occupy 250 bytes. So that's 500K. The index will take up 250K. But that's not exactly the math when you're calculating it. That's how you should do it. So therefore, there ends up being a case where if you have too many indexes, you end up actually having indexes that occupy more room than the actual table. Because if I have an index that's just for the name, it'll be 250K. Then I create a multi-column index, name plus phone number. That means that the second index could be 400K. And then we have another index, say it's name and postal code. And that one could be 500K. We add it all up. Right, so 1,150K, the database, the table is only 500K. Indexes grow really fast. Essentially, what you want to take away from it is that with indexes, you don't want to have too many. You want to have just enough. How do you know you have just enough? When access to the database is reasonable and it performs fairly well, but it's, you covered 90% of the cases. If the odd query is a little slower than the rest, that's life. Unless, it's an odd query for the person that signs your checks, then you probably want to make sure that one runs fast. Just putting it out there, it's a thought. You have to know your target audience. For example, if an accounting system and the query that pulls up the set of books is slow, you probably want to index that. If the query that comes up with the list of employees is a little slow, it might not be as important because, how many times you need to pull up a list of employees? You might have, 100 employees, 150 employees. We're not talking about Phoenix. There's tens of thousands of employees, hundreds of thousands. So in that case, you'd probably want to index the employees also because there's so many. You have to just make the decisions based on the data you have in your database. So unique and non-unique indexes. A unique index ensures that you can't insert duplicate values. That's pretty much like what your primary key does. Sometimes on a use table, you'll want to create a unique index on their username or maybe on their email address so you can't enter duplicate values. It helps keep the data clean. It also makes the searches fast. Or you can create non-unique indexes. For example, used for searching for individual entities, or where you want to do a group by. We were doing an aggregate earlier. We're grouping by. And let's say you're grouping by the product as opposed to the order. You want to know how many times each product is sold. You create an index on that so that you can summarize quicker based on that. All right, 2 more slides, and these ones are actually just rules. Rules for using indexes. Use them on bigger tables. Why? Makes things go faster. You always index the primary key, but since primary keys are indexed automatically, that goes without saying. Fields you search often on. email address, phone numbers, product codes. If you order by and group by often, those are the fields you want to index. When there are more than 100 values, you probably want to create an index, but not if there's less than 30, because that's pointless. Avoid indexes for fields with long values. Let's just say a name isn't a long value, but if let's say you get a field that has this atrociously long value, you don't want to index it. You probably want to hash it somehow first. If the key is used to figure out where a record is, use something else, like a sequence number. Well, it says Postgres uses sequences for its primary keys anyways. It kills two birds with one stone. Some servers have limits of how many indexes you can create per table, and literally how much space each given index can be. So you have to be careful. Otherwise, you might shoot yourself in the foot. Also, be careful, and you should not index fields that have null values. So if you have an optional field like email is not null, but phone number is null, don't index the phone number field because the null values will screw things up. Records that have a null value will not be indexed at all in that index. So suddenly records disappear out of the index, and what happens is it says, oh, I can't find it in the index. Never mind, we're going to go do a full table scan instead. So you did first a search against the index, didn't find anything, then it'll do a full table scan. If it allows null values, don't use those indexes. There. That was painful enough for everyone, including me.